All right, now that we have introduced the idea of energy and the concept of work, we are going to today think about and discuss a new type of energy, a new form of energy called potential energy. And we're going to see how that's connected to the work that particular forces do on an object. So I'm going to start with a work example. And the work I'm going to calculate here is the work done by gravity on this block. So this block is 1 meter above the ground, and the block is going to get released from rest, and the block is going to accelerate downward. And right before the block hits the ground, I'm interested in asking how much work has gravity done during this process as the block falls to the ground. All right, so remember our formal definition for work is the dot product between the force being applied and the displacement vector, and then integrating that over the entire path over which the object travels. So the work done by gravity, well, I'm starting 1 meter above the ground, and then I'm ending at the ground. So my integral is going to go from y position of 1 meter to y position of 0 meters, right, going to the ground. I'm picking the ground as my y equals 0. The force that's being applied to the object is the force due to gravity. So that is in the minus j hat direction. It's in the negative y direction. And the magnitude is mg. And then the displacement vector, that's dy, right? We're moving in the y direction. And so this dot product then, j dot into j, just gives us mg dy. And then when we integrate that, when you integrate dy, you just get y. And so here I have the integral, and then I've got to evaluate at the two bounds. So I plug in 0. Of course, that's going to give me 0. And then minus 1, but then there's a minus sign because it's 0 minus 1. And I get a total work done by gravity of plus 9.8 joules. So positive amount of work done because the displacement vector and the force vector are in the same direction. And of course, if we think about the work energy theorem, since gravity has done work on this object, the kinetic energy of the object is going to change, right? So the kinetic energy of the object at the end is 9.8 joules, more than what it started with, and since it started from rest, the final kinetic energy will be 9.8 joules. So now let's look at a similar example, but slightly different. I've got my block, same block, 1 meter above the ground, but now along a ramp. And for this example, we're just going to ignore friction, so there's no friction on the ramp. And so I'm going to release this block from rest, and of course it's going to accelerate down the ramp. And I want to know, when it gets down to the bottom here, how much work has gravity done as the block moved from a y height of 1 meter above the ground to y equals 0 at the bottom. Now, that was in my traditional coordinate system. I'm just going to set up in a rotated coordinate system just to demonstrate typically how we deal with ramps. So my force due to gravity, well, along my x-axis, which is the direction of the displacement, it's only the component of the weight down the ramp. So that's mg sine 30 degrees, right? That's the force vector points straight down. There's a component of the weight that points down the ramp. And that's in the I hat direction because I've chosen down the ramp to be plus x. The displacement, again, is along the ramp, down the ramp, so that's dx in the I hat direction. And then my bounds here, well, I'm starting up here, which I'm going to call 0. So this is my x equals 0, I guess right there. And then I end some distance over here. Well, I know that the height is 1 meter, and so that means this distance traveled over here is going to be 1 meter divided by sine 30. So when I dot I into I, that just equals 1, and so I've got mg sine 30, and then evaluating the integral dx, I just get x. And now I've got to plug in the values, and of course you'll see the sine 30s cancel out over here, and you get that the total amount of work done is 9.8 joules. And so even though my block went down the ramp, the change in the height of the block in both cases was exactly the same. We started 1 meter above the ground, we ended at the ground, and so in both cases the work done by gravity ends up being 9.8 joules. And again, if we ignore friction here, then the work done by gravity's got to equal the change in the kinetic energy of the object, and so the kinetic energy of the block at the bottom of the ramp is 9.8 joules. So if the work done by your force is path independent, so it didn't matter how my block went from 1 meter above the ground to the ground, it didn't matter if it dropped straight down or if it went down this ramp, the work done by gravity was exactly the same. And so if the force responsible for the work you're calculating, if that work being done is independent of the path which the object takes, then that force is known as conservative. And so conservative forces that we're going to see in 101 are gravity, of course, I'm giving this example, but also spring force. And then in 102, when we start dealing with the electric force, we'll look at that being a conservative force. Now, if the force you're dealing with is conservative, then we can define something called potential energy. And so the way that we're going to define potential energy is sort of with the work definition. So our work definition, as we go from the work done as we go from A to B, is just the dot product of the force dotted into the displacement vector over the path from A to B. We integrate that whole thing. And the potential energy then is defined as the difference between the potential energy at the start, A, minus the potential energy at the end. So that's equal to the work done. So the potential energy is related to the work. Now, the way that you see this in the book is that it's listed as delta U AB, so U is for potential energy, and so the potential energy, the difference as you go from A to B, well, when we do this difference, we do the final, so the potential energy at B minus the potential energy at A. And if you look up here, that's the opposite, right? This is B minus A, and up here I had A minus B. And so that means the change in the potential energy, B minus A, has to be equal to the negative of this. So that's negative the work done as you go from A to B. And so this is potential energy. Again, it's another form of energy, so the unit is joule. An interesting thing is that if you want to determine, if you know the potential energy and you want to determine the force, you take the derivative of the potential energy function with a negative sign, and that gives you the force expression for a given force. So since force is a vector, you can actually do this for, if your force is one-dimensional, you would just have maybe the x component, but if you've got 3 dimensions, then you end up taking the derivative with respect to all 3 different dimensions, and that's how you get your x component, your y component, and your z component. So potential energy depends on position, and we've been talking about position early on with motion. Position is arbitrary, right? You get to choose your coordinate system and your origin however you want. Since position is arbitrary, it's actually the change in potential energy that is going to be most useful for us when we look at problems and analyze the changes in energy over the motion of an object. All right, so we've got 2 types of potential energy that we're going to be dealing with in 101. The first is gravitational potential energy. Potential energy designated with a U, I'm going to use a subscript G for gravity, and the functional form for potential energy due to gravity is mgy. So what's the mass of the object? G, the gravitational, the acceleration due to gravity near the surface of, in most cases, the Earth, and then y, the vertical position of the object. And then there's this ambiguity here, plus some constant. And the constant is because you get to choose whatever you want to pick as y equals 0, right? Position is arbitrary. So wherever you pick as your y equals 0, that's going to set basically what this constant is. The point, though, is that if you compare the potential energy at two different locations, let's say as we go from A to B, well, then the potential energy at B is mgyb plus our constant, and then minus our potential energy at A, mgya, plus the constant. And since we're taking the difference, the constant terms cancel out, and what you get at the end is just mg times the change in the position. All right, so again, what we care about ultimately is going to be how the potential energy changes, not what the potential energy is at any given instant, because again, it's arbitrary. You could always pick your origin such that the potential energy at any given moment is 0. What we care about is how that changes, so the difference in potential energy at two different times or positions. So in addition to gravity, we've got springs. So there's spring potential energy, and the functional form for spring potential energy is 1/2 kx squared, again, plus a constant. K is the spring constant for the particular spring, so that depends on the physical properties of the spring itself. And x is the position of the spring. You can think of it as the position of the end of the spring. And again, you get to choose what you're calling that position at the end of the spring. And so it's typical that you would call the equilibrium length, that is the length of the spring without any stress, you would call that x equals 0. So then any stretching or compressing of the spring would correspond to potential energy being stored in the spring. When the spring is in equilibrium, not stretched or compressed, it's typical to call that 0 potential energy. So the big thing here is that we introduced work in the previous chapter. If you've got a force being applied to an object, that object undergoes some displacement, and so the force and the displacement are in the same direction, you're going to get work. Well, that is still the case, but what we're going to do moving forward is that if our force is conservative, so basically gravity or spring force, if those forces are conservative, we are going to track how the potential energy changes as opposed to the work that's being done. Right? And so it's the exact same approach, it's just now we're going to be sort of keeping track of potential energy rather than the work done by the force of gravity or the work done by the spring.